All right. Well, while people are filing in virtually, I'll get us started. Welcome everyone to the next installment in the ISCN, AGU, and USDA Climate Center's supported webinar series on soil carbon and its role in climate mitigation. Today in this webinar, we'll cover a major question that I think will be broadly interesting. How does tillage management affect soil carbon and the climate system more broadly? And I'll just introduce myself briefly first. I'm Eric Slesarev. I'm a postdoc at Lawrence Livermore National Laboratory and the Soil Health Coordinator for the International Soil Carbon Network. I'll be hosting today, and we'll be joined by Stephen Ogle, who's a professor and senior research scientist at Colorado State University. Stephen's research deals with greenhouse gas emissions from agricultural, forestry, and other land uses. And he served as the lead technical compiler for the U.S. National Inventory of Soil-Related Greenhouse Gas Emissions from Agricultural Lands, and is a coordinating lead author on the 2019 refinement of the 2006 IPCC guidelines for national greenhouse gas inventories. We'll also be joined by Humberto Blanco-Canqui, who is a professor in the Department of Agronomy and Horticulture at the University of Nebraska, Lincoln. His research emphasizes scientific principles of soil management and applied soil physics, and his research contributions span widely. They include crop residue management, cover crops, conservation tillage, dedicated energy crops, biochar, and other organic amendments. With that brief introduction, we'll start with the first speaker, who will be Stephen. We'll have a 20-minute talk followed by 8 minutes for questions, and then the second talk, Humberto, will go after that. Throughout either talk and during the Q&A sessions, you're welcome to submit questions via the questions feature that you'll find in your GoToWebinar control panel, and then I will moderate those questions and select some to offer up to the speakers, in addition to questions that might have emerged during the registration process. So without further ado, Stephen, take it over.
Thank you, Eric. I really appreciate the opportunity to speak today on this topic, which has been central to research I've done over the years. So when we think about no-till farming, there's a few things we need to keep in mind here. No-till kind of evolved as a way to reduce soil loss due to intensive tillage. It didn't really become feasible until we had herbicide development post-World War II. And then there was expanding adoption in many regions of the world in the latter part of the 1900s. Arguably, the main benefit is to reduce soil erosion, but there are other soil-related co-benefits, including enhanced soil organic matter, which is the topic of the discussion today, enhanced water retention, and enhanced fertility. Early on, initial syntheses supported the idea that there was a benefit from a climate benefit, if you will, of no-till management. And one of the, I would say, major syntheses of the time was done by Tris West and Mac Post. And if you look at this diagram on the left side here, this is the soil organic carbon using no-till on the y-axis and conventional till on the x. And basically, they were showing that there is an increase at the surface of these soils. As you go deeper, there's less change. And they estimated on average there's a little over half a ton of carbon per hectare per year carbon sequestration in soils when you adopted no-till. They did note that in weak fallow systems, there didn't seem to be an increase as an exception to that finding. They also noted, you see in the graph on the right side, that this effect is transient. Really, after about 20 years, there's very limited impact beyond that, although it doesn't mean there's zero change, but it's much reduced. At the same time, there was work trying to understand the mechanisms driving this, and Johann Six and his colleagues looked at this, looked at microaggregates within macroaggregates, and this was a model diagram of their model, in which over time, if you look on the left-hand side there, basically you have these macroaggregates that are formed in the soil. Microaggregates are within that, and within those microaggregates, you're protecting particular organic matter. Now, if you till that soil, say at time 2 there, you break up that macroaggregate, and that protection to the palm is no longer there, and you get increased decomposition and ultimately less carbon in the soil. I was part of a group around 2004 that was working on the National Greenhouse Gas Inventory Guidelines that were published in 2006. And we knew that we needed to estimate factors for the methods in those guidelines. And one of the things we wanted to capture was the influence of no-till. There's a paper we published in 2005 on a synthesis we did at the time in the Journal of Biogeochemistry. And we'll focus on no-till here. You'll see that in the top, there's these response ratios. That's the amount of carbon in no-till divided in the no-till plot divided by the amount of carbon in your control or full-till plot. You see most of those response ratios are above 1, meaning more carbon in no-till. We derived factors, you can see in the lower graph there, and found that there was a difference in climates. In tropical moist particular, there was a gain, the factor was 1.23, a gain of 23% increase in carbon with no-till adoption over 20 years, and the lowest was a 10% gain, a factor of 1.1 in temperate dry climates. So we thought we understood this pretty well at the time, but then scientists started asking the question, what do we really know about the climate benefit of no-till management? And certainly a question we should always be asking of our science. Do we really understand the dynamics? In particular, John Baker had a provocative article, as well as Dave Powelson out of the UK also had an article on this. And just looking back at Baker's article for a moment, one of the things he noted is that when we look at the studies on the right panel there, the studies that West and Post had included in their meta-analysis, you can see none of those go below 30 centimeters. That was the objective of that particular synthesis. But when you look at the root growth of maize or corn on the left side, it grows much deeper than 30 centimeters. And his question is, are we impacting that growth in some way? And so there could be impacts deeper than 30 centimeters. At the same time, it was recognized that when we plow soils, we change the bulk density. In particular with no-till, one of the problems is you can compact the soil, increasing the bulk density over time, and this can lead to problems with using no-till continuously. But this wasn't addressed in those early syntheses, not in the one I did, nor the one that West and Post or others had done at the time. So people started talking about we need to look at equivalent soil mass. The other thing about tillage is it's moving residues deeper in the profile. And because of that, you get redistribution of carbon. And those residues are moving down, the plow layer, maybe a little bit below that, where you're building up carbon, and that could be below 30 centimeters. So Denny J and his colleagues in 2008 took another look at this with long-term experiments, some of our best experiments for evaluating this, and they looked at a ratio of no-till minus full inversion tillage divided by full inversion tillage. So values to the 1, which would be to the right of this graph, is more carbon in no-till. Ones to the left, or negative values, is more carbon in your full inversion tillage. And sure enough, they did find more carbon at the surface as we go down the depth on the x-axis here. But as we get down to around 20 centimeters and going down to 40 centimeters, they found that there was more carbon in the full inversion tillage. Now, when they aggregated this across the profile, they still found a benefit of no-till, but it was reduced relative to what West and Post had estimated. Liu et al. Followed this up with a study, a meta-analysis published in 2010, and they concluded in the separate meta-analysis that even though there is a benefit at the surface, this increase at depth down around 20 to 30, 40 centimeters is offsetting that, and there's no significant difference across the profile. Well, Kravchenko and Robertson a year later looked at this again and said, well, what can we really say about what's going on at depth? What's our power? Statisticians call this type 2 error. And they found if we aggregate to the whole profile, we need considerably more replicates than we typically have in their experiments to even find a 50% difference in carbon change, which we don't have with no-till. None of the studies have suggested that create a change. But even with that large a change, we would need many replicates. And so this began to ask the question about, should we be aggregating the soil layers, and do we know enough to say what's going on at depth? In 2017, I was again involved with an IPCC report on soil carbon and other greenhouse gas emissions to update the National Greenhouse Gas Inventory Guidelines. There were many comments early in that process that came in from the community that says you need to reanalyze these tillage factors. And we agreed. As authors, we saw a need for that as well. And so we synthesized the data at that time, which included many of the studies in these earlier syntheses, but also newer studies. And there are a couple things we did in these syntheses, that I think are important to point out here. One is we analyzed the effect specific to every centimeter, if you will, in the soil. We did not aggregate the soil. We did not analyze just the whole profile. We wanted to estimate the specific impact at each depth in this analysis. And the other thing I'd point out is we did an adjustment for the soil mass, because we knew that was also important, and we did that in this analysis. I don't have time to talk about all these results today, but when you look at these red lines here, those are our depth increments. You'll notice we were particularly interested in difference in climate and soils combinations around the world. And you'll see some of these have many more observations or measurements, if you will, from experiments than others. Some of them are actually quite lean. You notice, of course, at the surface, we conclude, as other studies before, that there was an effect at the surface. But as you go deep in the profile, 20 to 40 centimeters, you see an increase in carbon with the full till system. Notice as you go out further in the depth there on the x-axis, you get out to 50, 60, 80 centimeters, the uncertainties are large in most of these climate and soil combinations. One could conclude, because those uncertainties so large, clearly including zero, that maybe there's no significant impact to tillage. But I would tend to defer here that we still don't have enough observations at depth really to say what's going on deeper in the profile. But nonetheless, there is an effect down below the plow layer in the subsoil, and that was pretty clear. So we took, for each of these climate and soil combinations, down to the depth where there was a significant difference between the two tillage treatments, and estimated the cumulative soil carbon stock. And that's what I have in this diagram. And if we start from the bottom, and this is the soil carbon stock change on the y-axis and the climates, if we start with these cool climates at the bottom, you'll see that most of those include a value of 0. So at this 95% confidence level, we can't eliminate the possibility that there's no change between the two of them. If we go to the cool, moist, sandy, it does appear there is a change, but it's getting pretty close to 0 in that confidence interval. If we move up to the warm climates, warm temperate climates, you'll see there the sandy, or the warm temperate dry does include 0, but if we move into the warm temperate moist there, both of those confidence intervals do not include 0. And that warm moist, and I should have pointed this out, the S is the sandy soils and the LSC is the loamy silting clay soils. Those sandy soils seem to have a bigger benefit, around the half a ton that West and Post had said in their original meta-analysis there. If we look up to the tropical soils, most of them do not include the 0 value. Some of those increases up around a half a ton, so more significant impacts in the tropical regions. But the bottom line here is when we went back to re-estimate these versus what we had done in the 2006 guidelines, those factors were reduced by a half or more, and there was more uncertainty in a lot. So not as significant an impact, although still in some region there is a significant impact to no-till. Well, there are other things that we should be considering when evaluating this climate benefit of no-till. And one is thinking about the lateral transport erosion deposition. Many of the studies that we use from these long-term experiments are on rather flat terrain, and so they're not on depositional sites or eroding sites. And many of you probably recall an article by Van Oost et al. In 2007, rather provocative article, that when you're tilling the soil and you're increasing erosion, you actually get an increase in carbon across the landscape. And there was 2 reasons for this, according to their analysis. They were using cesium isotope data there, is that carbon that's eroding is going to a depositional zone and being buried there, and it's increasing carbon in that area. But also on that eroding slope, you're getting increasing carbon as well, because you're replacing a dynamic, they call it dynamic replacement of carbon over time, as you're moving subsoil up that can better stabilize that carbon coming in the soil. Well, what does this mean for conservation tillage? That was a question I had at the time. I remember talking to Van Oost at a meeting, I believe it was at AGU, and then a little later they came out with an article. It was led by Quentin, but Van Oost was a lead on this, or another author on this article as well. And this diagram kind of illustrates the point I want to make here. You've got carbon residence time, and that carbon residence time declines as erosion rate goes up on that eroding area. And this, what's occurring on this eroding area is really important here in terms of whether you have a sink or not across the landscape. And so if we look at cropland under conservation, which would include no-till, and then cropland that's not under conservation, more intensively managed, if we have a high input system, that green there means there's a sink. Okay, and you'll notice if you go to more intensively out at the end there, you have a larger green half circle. That means there's a larger sink, according to them. And then if you have low input though, and you intensively manage it, then you get a source when you're doing that, as opposed to conservation. Okay, so what does this mean? High input, low input. High input to them was that you're not having an effect on the crop production with erosion. Okay, many times we will have an effect when we're eroding an area. We will get less production there. And so that's really important for us to keep in mind. If we're doing no-till in a landscape, we were doing conventional or full till before, and all of a sudden we introduce no-till, and it's not affecting the yields in a significant way, then we may have had more carbon in the landscape before when we're using the conventional practice. Whereas if we are having an impact on the production, because with the erosion there's less production, then we may in fact be increasing carbon across that landscape. Another thing, briefly here I mentioned, is nitrous oxide emissions. This is an article by Van Kessel et al. In 2013, and I have you focus here on the A plot, in which those positive values means there's an increase in N2O emissions, and they group no-till and reduced-till here. And then a negative value means a decrease. In a dry climate, this seems to be important. When it's less than 10 years from the time you adopt no-till, there appears to be an increase in N2O emissions. Then after you get past that 10-year mark, there seems to be a decline in N2O emissions. And this is speculated that this has to do with the bulk density, changing water dynamics in the soil. Unfortunately, I don't have time to talk about the others, but they also showed some crop yield effects, and they looked at that relative to the N2O emissions. Finally, one more thing I'd like to point out is rotational no-till with intermittent no-tillage. And so one study by Van den Bijgaard and Kay around 2004, they were looking at it. They plowed a field that had been no-till for a while, and they followed that for about 17 months. And they found that 3 of the soils that they were looking at didn't have a significant change in carbon over time. But one of these soils, it was the sandy loam with low carbon. They did see a decline, about 3.5 tons of carbon per hectare. Unfortunately, there aren't many studies like this. So Conan et al. Around 2007 did a study, a model-based study, and they noted there from those model results that it really depends on how often you're doing this intermittent tillage, where you come in and use a moldboard plow or some other type of tillage implement. If you're not doing that very often, maybe out there in NT10, for example, is you're only doing the intermittent tillage about every 10 years, or you're using some type of cultivation device that is like a ripper or something that's not as intensive, then you're going to be pretty close to the full benefit. But if you're doing intermittent tillage every 2 or 4 years or so, you're really not getting a lot of benefit in those cases. So just a few conclusions I'd like to make before I hand it over to the other speaker. The climate benefit of no-till really depends. I can't come here today and say, yeah, there is a climate benefit. We are increasing soil carbon. We are either not infecting N2O or we're reducing N2O. It really depends on the climate and soil types, as we showed in that review back for the 2019 IPCC report. It also, I didn't talk about cropping intensity and rotation, but there are some impacts there. For example, West and Post talked about when you have a fallow in the system, it doesn't seem like no-till has much of an impact. Also, that study by Liu et al. Suggested that if you're doing a double cropping in a year, you get an impact in no-till. Even though overall you don't, but if you're doing the double cropping, they did find an impact. Erosion and deposition has an impact, as I just discussed. Nitrous oxide emissions can increase, it appears, in these dry climates, and also the continuity of that no-till management. The last point I'd like to make here is there's large uncertainties. If you remember back the diagram I showed you from our synthesis, those error bars were quite large in terms of the no-till benefit for climate. And there's risk there in meeting greenhouse gas mitigation goals, as you know, the Biden administration has been promoting carbon sequestration in soils as part of their plan for the Paris Agreement. We have to manage those uncertainties in some ways to limit that risk, I think. One way is to get more farmers to adopt and try to avoid those areas maybe where we're not going to have the climate benefit. Now, I wouldn't argue here that we don't want to do no-till for reducing soil erosion. And I think that's far more important for longer term sustainability of these lands than for production than any carbon benefit we're talking about at the moment. But anyway, we need to manage that risk. The other thing I would say is we don't have a lot of observations. We have about 100, I would say, high quality experiments we can use to parameterize and test our models, but that's not many, particularly when you think about the US, and we literally have hundreds of millions of hectares of agricultural land. This is something we really need to rectify and have more observations out there, and some more experiments as well. So some experiments in strategic areas to answer questions that we still have, but also a monitoring network across a much larger area, something like what the National Weather Service has with weather. Maybe not that many as they have with weather stations, but certainly more than the 100 we have at the moment. And the other thing is, of course, continue to better understand the mechanisms, particularly what's going on at depth. So I thank you for your attention. I think there is a little time for questions here.
Terrific. Thanks. Yeah, there's plenty of time for questions. So I'll start with ones that we just got from the audience here. The first question relates to the results in the 2019 meta-analysis that you showed. And the question is, what are the sources of uncertainty in the meta-analysis? If I can add to that, I guess I'm sort of curious if you can give a sort of non-technical explanation of how you managed to develop those uncertainty bands in a way that was continuous, since that's not something that's done very often.
Yeah, that's a good question. So maybe I'll start with that question and then I'll talk about the sources, or maybe I'll try to answer them at the same time. So there's variability in the measurements that we have, and that's driving a lot of this uncertainty that we found that we had in those bands. And the variability, and then limited measurements. You know, I'm speculating here, but I would say if we had 5 to 10 times as many studies, those uncertainty bands would be a lot less than they are. But nonetheless, we have the data that we have. The way we developed this model was a semi-parametric modeling approach. And I'm going to start by saying I'm not the statistician on this analysis. I did have a statistician, he's a co-author on the paper. But basically, he was looking at putting, if you will, knots into the regression. And so he would fit this, and he would allow with splines to adjust that curve as you move across depth. And that gave us a continuous surface. And if you think about it, any particular centimeter in the soil, whether we're at 5 centimeters or 15, we have a set of observations there from those increments. We didn't aggregate them anyway, but we have a set of observations there. And that's what that regression is fitting through, that semi-parametric regression approach that he used. And maybe I better stop there because I'm not the statistician on the analysis. And further, I might be getting into too much technical detail for the group today.
No, that's great. That gives a general sense of how it worked. Thanks.
One other thing I should mention also, there in the error adjustment for mass equivalency, there was a lot of uncertainty too, because it wasn't even quite half the studies that gave us enough information to calculate the mass equivalency. So we had to create a model to effectively fill the gaps for the rest of the data. And we didn't do that on the specific data, but we did it on the predictions. And that was an additional source of uncertainty in our analysis.
Yeah, all the more reason for people to publish their bulk density data and to collect it. All right, so this next question here, this is an interesting one. So the question is, would it be fair to say that more of the stock changes and dynamics are being driven by what's happening on the residue input or incorporation side rather than the stabilization or aggregation side? So yeah, can you speak to this balance between changes in inputs versus changes in outputs?
Yeah, that's an interesting question, and I may not be interpreting this correctly, but I'm gonna assume here for a minute, but you mean residue input. It's related to the crop production, which can change with no-till, and that was something that Van Kessel was showing, and some other papers they published showed that as well. But also where it's incorporated in the soil profile, if it's just sitting on the surface versus being incorporated deeper. And those are certainly important dynamics, without a doubt. But at the same time, no-till does increase aggregate formation and the stability of those over time, and that is protecting the carbon. I don't think anybody has necessarily refuted the work of Six and all, and others have done it since then and shown that yes, you do get stabilization of carbon in these soils from that. So I think the two are somewhat competing against each other, and it depends on the climate and soil, right, and the conditions. And in some case, moving it deeper is more important than the stabilization, but in other cases, there isn't. And these are really two mechanisms taken in opposite directions, and they're competing in a way with each other to determine the overall effect.
Great. Here's a question. I'm going to pluck this from farther down the list because it also came up in the registration responses. So the question is, based on the uncertainties highlighted, is it feasible to use tier 1/2 approaches, non-measurement based, for soil carbon crediting and monitoring, recording, and verification? And this relates to questions that came up in registration that asked about how we model the effects of no-till and how well connected the model responses are to the measurements.
Yeah. So I want to put my IPCC hat on here for a moment, and I'm going to tell you that tier 1 method is really developed so countries can do an inventory. It gives them an entry level. Those methods were never really intended to be used widely, and certainly not in carbon crediting. If that source is important, because it's a key source in your country, meaning there's high level of emissions or there's a dramatic shift or trend in those emissions over time, you need to go to tier 2 or tier 3. And so I would say for carbon markets or carbon crediting of some kind, you at least need a tier 2 where you've estimated factors more specific to your area. Remember, these are global factors. They don't necessarily represent any one area that well. They're averages across a large area. So that'd be kind of my response to the first question. The second part of that question there, I would say, yeah, models will tend to they're deterministic, most of the models we're using. And so they often predict an increase in carbon with no-till. Not always, though. We do have runs, particularly if we're having an effect on production, although our models are not maybe as sensitive as they should be, particularly our ecosystem models. I know crop models are more sensitive, but we have to remember there's uncertainty there. And that's what I always tell people. Okay, that's the estimate, but look at the uncertainty, because that uncertainty often, if there's a lot of uncertainty, may include a gain or loss in carbon, maybe telling you that. And so even though the model's not directly giving you that inference, the uncertainty is, and we need to use that to inform our decisions.
Okay, here's another question. This is an interesting one too. Do you think there's publication bias in the literature, and how would this affect meta-analyses, and how can we manage publication bias?
That's a really good question. I would say yes, there probably is. We're more likely to publish if we get a significant result than if we don't get a significant result. Editors are more interested in publishing the papers with significance. Yeah, I don't know how to manage that. Where do we go with their non-significant results? I think that's a difficult question, but maybe I'll answer this in a different way. I think when we get into policy and management and carbon markets and things, there really needs to be a monitoring of that carbon. So we've learned what we learned from the literature, and we've done our meta-analyses, and we've done studies to understand the mechanism. I think it's very important to follow up and understand the mechanism, not just to get an empirical result, but understand why you're getting that empirical result. But a monitoring network is very important here, and I kind of alluded to that in my conclusions. For example, if USDA moves forward with a program encouraging carbon sequestration in soils, and we have 100 experiments out there really evaluating, we need a lot of sites then to monitor and follow up and make sure that we're getting the carbon sequestration that we expect. And that would also help us much better parameterize our models, much as the National Weather Service does with their weather models. We may complain about their forecasts from time to time, but if they had 100 weather sites around the country, it would be a lot worse. I can guarantee you that. They wouldn't do nearly as well. So we need monitoring, a statistically based design to that monitoring too, so we can have a statistical inference on those on what we get out of the monitoring network.
I think we can all agree on this. We'd like more data.
Yeah.
All right. Well, I think in the interest of keeping on schedule, we'll move on to the next talk. So we'll pass the screen over to Humberto. which hopefully goes off without a hitch, but you never know with these things.
That's right. Okay.
And while we're waiting for this transition, I'll sift through the questions. Oh, okay, it looks like we're on track. I'm seeing, there we go. Oh,
Okay.
it flashed back and forth. Now I'm seeing the editing view, but
Let's see. What about now?
that looks good right there. Yeah, perfect.
Okay.
All right, take it away, Humberto.
Let's see here. Minimize. I don't see the full screen. It disappeared for some reason.
Well, I can see the presentation.
Yep.
On my end
I got it.
I think it's okay.
Great.
All right.
So we have this question, right? Does no-till store more carbon than conventional till? I'll be using the phrase CT, or the abbreviation CT from now on. Stephen did a great job in terms of summarizing previous studies. You know, some publications came out in early 2000 and that showed the potential of no-till for accumulating carbon compared to CT. But now it's about 20 years later, and it's obviously there's a lot of excitement or enthusiasm out there, and I guess we need to re-examine the potential of no-till. So I'll be presenting research data, in other words, experimental data. Okay. And this can be used to compare against model data or opinion-based information, right? So what do we really know about the potential of no-till, like Dr. Baker suggested about 15 years ago? So let's revisit. Some of the reviews, I think I missed one or two, but the conclusion is the same. This is what we know. Dr. Baker in 2017 really, sounded the horn, right? Saying what do we really know about carbon sequestration with no-till? But he concluded saying that, you know what, there are no, in general, right? In general, there are no differences in carbon stocks between no-till and CT. Then in 2009, Govertz and et al. Did a global review of studies available at that time, and then found that no-till increased carbon in about 50% of studies, but that was mostly in the upper 20 or 30 centimeter depth. And actually no-till reduced carbon in 10% of cases. And in 40% of cases, there was no difference between no-till and CT. And then Liu in 2010 found no differences as well between no-till and CT for the whole profile. What's the whole profile? It's some studies have sampled down to 60 centimeters or some to 100 centimeters, about 1 meter. Okay. Then recently, Hathaway et al. Looked at a bit more in detail how tillage intensity affects carbon accumulation, because a lot of times we compare no-till against small-word plow, which are two extremes, right? And then what about then systems in between? But again, they found that there are no differences in carbon stock between NT and CT for the whole profile. We did measured carbon stocks when I was a research scientist at Ohio State from 11 on-farm sites. So we had sites, one in each MLRA. So we have the number of states, Kentucky, Ohio, Pennsylvania. So 11 sites, on-farm sites. These are paired sites, obviously not randomized experiments, but they are paired, they are next to each other. what we found is that no-till, yes, can store more carbon than CT in 50% of cases, but that's only in the upper 10 centimeters or 4 inches. What about in the rest? Well, no-till, I put it red here, less tended or had significantly lower, in some cases tended, no significant differences, but in 6 out of 11, about 50% of cases, below 10 centimeters. So it flipped, right? No-till was better in the upper 4, but CT was better below. Then for the whole, let's call it for the whole profile, there was no difference between NT and CT. A similar study by Christopher et al. With different MLRAs in the eastern US found the following. I highlighted the abstract, the key sentence. But in other words, what they found is that in the upper 60 centimeters, there was no difference between no-till and CT in about 80% of cases, right? And then they even concluded here that the total profile was actually greater under CT than NT in 3 MLRAs, right? So, but in short, there was no difference in NT and CT. Okay, so we have a good number of reviews and some site-specific studies. I think from my humble understanding of the literature, review papers and research articles that have been published in the past 20 or 25 years specifically, with no-till and carbon storage, is that yes, no-till can store more carbon, store more carbon than CT near the surface in the upper 2-4 inches. But the opposite could be true in some cases at the bottom of the layer where we plow, right? Because we are, burying residues at the bottom of the plow layer. When we add the layers, the summation shows that there are no differences between NT and CT for the whole profile. Remember, I'm using this in general. In a few cases, may be. Yes, and that's true. No-till impacts seem to be highly site-specific. While in most cases, no-till may not outperform CT, but in some cases, it does. But that's not in general, in a few cases. And this seems to be in accord with some of the papers that came out in recent years, saying, let's get realistic. The myth of no-till, limited potential. Then when I read these papers, I said, oops, these are some opinion papers. Maybe, well, not really. They're based on research data, on the reviews that I published and the research papers. So they seem to reflect the reality. And our review on research papers also seem to agree with the recent review on occasional tillage of no-till soils. Well, there's a lot of talk out there. Okay, we have herbicide-resistant weeds, some compaction, nutrient stratification, right? Acidification. How can we manage that under no-till? Should we plow once? How often? Well, what about if we plow 1 in 5 years or 1 in 10 years? And that's what led to this review. So we reviewed all the published studies. We have a good number of studies from Australia and from the States, and I highlighted what we found after doing a global lit review on occasional tillage effects on carbon stocks is that occasional tillage, again, not every year, not every other year, not every 2 years, every once in 5 years and 10 years, does not reduce carbon stocks, but actually it's a good thing. It will reduce the vertical stratification. It may bury the improved layers to lower depths. So yeah, and that's how it is when it comes to carbon. What about other issues like erosion? Yeah, so could be negative. Maybe if it rains after plowing or the soil surface dries out and there's a windstorm, we might lose some soil. But the idea that one-time tillage, again, once in, let's say, in 10 years, will erase all the benefits of no-till on carbon, it's not supported by literature. Well, that's where I can stop, right? Well, the no-till doesn't work. It's the same as conventional till. I don't think so. There are spots probably where no-till can work. Where and when and where can I use no-till? What about if we consider these factors? What about climate? That is precipitation amount, right? What about initial carbon level? What about no-till duration? Textural class? Slope? What about the cropping system? Cropping system, I mean, we tend to assume that when we switch from plow till to no-till, you just solve all your problems, which is not the case. Here I have some photos from Western Kansas, one photo there. This is a no-till system. No-till system there, I don't see a lot of residue left there. It's a fallow. Sometimes we bale residues for our cows, right? Or maybe corn silage. All of these systems are no-till, but the cropping system will have an effect, right? So what about if we look at these factors? So one question is, does climate affect the no-till, effect on carbon sequestration? One may be quick to answer this, say yes. Liang et al. In Canada, this group did a review of all studies. I'm talking about the no-till compared with CT studies in Canada. So what they suggested is that no-till, yes, can store more carbon in semi-arid climates, but not in eastern Canada. So, and an interesting finding there. It's not unique. I mean, others have suggested that as well. So this is related to low carbon soil. Soils in semi-arid regions tend to have low amounts of carbon, right? Then that would be, the ideal scenario for carbon accumulation. Remember that carbon saturation is key for carbon accumulation. But this seems to contrast. Obviously, it's only 3 studies. For our study in Central Great Plains, obviously this is not semi-arid, right? In Hutchinson, we have 3 sites: Hutchinson, Hayes, and Tribune. This is not technically, it's not semi-arid. I mean, it's a semi-arid region is for precipitation below 500 millimeters. But here we do have one semi-arid region. It's a 20-year-old experiment, well randomized, and with 4 or 6 reps, if I remember. Then Tribune, this is the heart of the Central Great Plains. But no-till did not outperform CT. What about in Hayes, which is close to semi-arid region? No-till accumulated carbon in the upper 1 inch, nothing below. Here's the summation, 0 to 40, 60, there was nothing there. And in eastern Kansas, accumulated down to 2 inches, but that's it. So it seems, even in semi-arid regions, we may not see high carbon accumulation, even after 21 years. What about another question? So the longer I, use no-till, the better. Well, is that correct? So does no-till ability to sequester carbon increase with time after adoption? Well, not really. Actually, it can decrease. You may not see a lot of benefits in the first 3, 5, 6 years. It seems it peaks in 10 years, according to some reviews. And in some cases, it's up to 50. depending on the initial carbon level and saturation, right? But carbon accumulation with no till is not finite, right? It's finite. I mean, it's not infinite. It's not infinite, clearly. What about texture? What about comparing sandy soil against a clay soil? There are other research articles, but this review mentioned that, you know what, medium textured soils could accumulate more carbon than sandy or clay soils. Why would that be? Well, coarse soils are located in semi-arid regions in some cases. It can may not accumulate, it can lose. I mean, it can gain, but it can also lose carbon quickly, right? And fine textured soils may be close to saturation. So it's a medium textured soils may be the right environment for carbon sequestration. But again, this is not conclusive, could, right? What about slope? We have been putting these practices a lot of times, some improved management practices in highly fertile soils or flat soils. Why not target problem soils with no-till farming? You know what? Sloping soils can actually sequester more carbon than nearly level soils, according to a recent review, and we kind of knew this already, because flat soils tend to have a higher organic carbon level, and they are not susceptible to, for example, water erosion. But sloping soils are often eroded. Let's remember an article that came out a few months earlier this year from the Midwest, where sloping soils have lost almost the whole horizon. So I think there is an opportunity here, right? If we target sloping soils with improved management practices. So what is the sweet spot? What would be our favorite site to sequester carbon? If you want to adopt not only no-till, cover crops, even biochar, or perennial grasses, I think we need to target low carbon soils. Low carbon soil is just talk about one soil. And if somebody says, I do have a farm which has a low carbon, it's a sloping, it's eroded, and it's coarse textured, and it has very low biomass input at the moment. This is it. I think, not only I think, I would be happy to come out and establish an experiment there. I mean, there are also experiments already there, not maybe not many, showing the potential of no-till and other practices to increase carbon in this type of environment. Well, okay. This okay. It seems in general, what are you trying to get at here? It seems that no-till does not store more carbon than CT in most cases for the whole profile. So it's clear for me there based on literature. But should we stop there? How can we enhance the potential of no-till to sequester carbon? Biomass production is one of the key parameters, right? What about increasing above and below ground biomass, especially below ground biomass? What about adding cover crops? There are steps, right? No-till is, what about, that's the first step. The second step is what? No-till plus cover crops. The third step is no-till plus cover crops plus diverse vegetations or biochar, right? But not even that. It's easier said than done. I mean, if we terminate cover crops early in coarse soybean systems, this is what we get. It's not even 1 megagram. Now, if you terminate late, you get more biomass, but be careful. What about if it's a dry year? So it may affect subsequent crop. Maybe planting after silage in early September. What about planting in after wheat harvest in summer, and we get this much, right? That will accumulate some carbon. Combination is needed, right? Well, what do you learn from this? Unfortunately, you might say that, my conclusion is that no-till has limited potential to store carbon relative to CT. Yes, it can store in some cases, but that's minority. I mean, in general, does not seem to store more carbon than CT. So what about climate change mitigation then? Well, its potential, Notill potential is highly questionable. What about if we enhance, let's add some companion practices. Yes, can help. Cover crops, right? They're biochar, but there is a but there, right? I mean, is it easy to plant cover crops? What about the cost? What about the termination, planting dates? What about biochar? How expensive is it? Let's remember that no-till, why no-till was created. Was no-till created to sequester carbon? No, in the 1940s when I started with Faulkner and others, talked about developing no-till for conserving soil, reducing erosion, reducing evaporation, improving yields maybe in semi-arid regions. It has delivered. No-till is great. It has fulfilled its purpose. It can also be, a strategy to mitigate, heavy rainstorms, right? To droughts if we leave a lot of residues, right? Maybe flooding in some cases can reduce risks of flooding because it improves water infiltration in most cases, right? What about this production costs? That's another, right, component benefit. Conserves water. It can improve yields, especially in semi-arid regions, not in temperate regions. Rapid there's reviewed, right, the global data that no, it may not increase yields in temperate regions, but could in semi-arid regions, right? There are a lot of other benefits, and those benefits are enough to preach the good things about no-till. But the idea that that no-till will sequester large amounts of carbon after switching from plow-till to no-till, I don't think is supported by research data. That's all what I had. So I think we have enough time for some questions, right?
Great. Yep, that was perfect, and we're on schedule with time for questions. Thank you, Humberto.
Thank you.
So here's one question that came up early on. So when you were talking about occasional tillage, the time frame for occasional tillage was you mentioned was 5 years or so. The question is, what about occasional tillage at a 1 to 3 year time span? How frequent is too frequent?
Good. That's a great question. I guess I was asked about that when responding to the reviewer comments. Yeah, I think every other year or every 3 years probably is a bit too frequent. I'm thinking not only in terms of carbon sequestration, but also other benefits that no-till provides. I mean, like soil structure and water infiltration and water conservation, all that stuff. So probably the minimum number of years that we should wait is 5 years, but once in 5 years or 10 years seem to be okay based on data. One thing to clarify is that it's not like we have millions of paper on the topic either. A lot of researchers have done work in Australia and then some around here, but based on the available data, it seems that there are no large negative effects of plowing once in 10 years on carbon stocks. So.
Great. Here's another one. How does crop species affect no-till potential to store carbon? For instance, corn versus soybeans. So you talked about the input rate, but within conventional agricultural systems, is there an interaction with crop species?
Oh, definitely. Yeah. With the species, not only rotation, but soybean, we don't get a lot of biomass with soybean, so that decomposes much more quickly than corn stover. So then, but even corn, continuous corn systems, it's just one extreme there. Sometimes doesn't sequester a lot of carbon. So then we really need to diversify. I mean, we plant corn in May, and then we harvest in October, then we leave the land and fallow for 5-6 months, if not longer, right? So that's the spot where we need to grow something else. I mean, cover crops, right? Forage crops maybe, right? For cows and other, uses. I mean, so if we diversify that, let's say, okay, cover crop, this species is not working, right? Now let's add that. Let's add something different, like rye, cereal rye, right? After corn harvest, which is different, and even a mix, right? Although cover crop mixes may not outperform single species, but it is something that will diversify the system, which one is the next step of just no-till alone,
Great. I think that's a good answer to that question. Another one just popped up that I think is really interesting in its scope here. So this relates to the soil carbon debt of agriculture. To borrow a phrase from John Sanderman's paper on the topic. And the question is, hold on, it's disappeared here. If no-till can't help restore carbon, how did we lose nearly 50% of organic carbon from our grasslands during original conversion to ag land? Once it's lost, and we can restore with reducing disturbance. Is it strictly biomass inputs driving carbon sequestration? If no-till doesn't restore carbon, then why have soils lost carbon under cultivation is the question.
Yep. Yeah, so the cultivated soils have lost a lot of carbon due to disturbance and obviously elimination of perennial vegetation. I mean, the roots and the biomass. So I mean, the below ground biomass needs to be looked at in detail. So if we want to restore carbon, to its original, maybe that's not the objective. I mean, do we really go back to the native prairie, right? May not be. I mean, we talk a lot about this gap, right? Carbon gap or soil health gap. But if we want to restore some of the carbon lost, I mean, it's not only just reducing disturbance, right? There's also adding especially below ground biomass, but below ground biomass is the one that contributes the most to soil carbon, so yep. So definitely the diversification with the different plant species and, and in combination with reduced till can help to maintain the current carbon levels, because in some cases, if we are using no-till, but if we don't have enough even below ground biomass input, then probably we are losing, right? I mean, even though we are using no-till, I mean, we're still losing. There are studies like that looked at carbon on their no-till systems, so compared to plow-till, we may be gaining, but compared to the initial level, no-till one 10 years ago, 20 years ago, now we're still losing, right? So there are other pieces that we need to think about, like perennials and other companion practices.
Great. We've got a minute or so left. I'll sneak in one last question here. So I know you didn't address models directly in your talk, but I still think this is an interesting question. I'm curious to get your opinion on this. This question is, can you comment on how the models like Comet Farm, for instance, still suggest such large soil carbon gains from no-till? This is guiding both policy and market activity. So
yeah,
what's your guess? Why is there a disconnect between the models and the experimental evidence?
Excellent. That's a good question. Well, I'm not a modeler, but I know a little bit about models. I've used some water erosion models and also a bit played with century model. And one thing I know, and modelers can correct me, but for example, models do not model the stratification we're talking about, right? I mean, no-till stores near the surface in the upper 4 inches. What about below? Well, plow-till can store in some cases. I mean, can somebody correct me that, right? I mean, models, most of the time model for the upper 8 inches, okay? Well, then what about for the, for the whole profile, right? So models, when I've been talking to colleagues about the potential of models, I said, I've been told many times that models are models. Models are not supposed to be, not supposed to, match your measured data. They're supposed to simply estimates, like the previous speaker was talking about, right? And then there are, uncertainties with the model. So I would still preach, like measured data. There's no replacement for measured data. I mean, models, we are trying to approximate, natural conditions, but we're working, but still measured data, although we don't have like carbon data for every field, obviously, around the world, but for representative soils around the world, we do have some, and that suggests that Notill does not seem to outperform CT in most cases.
Great, thanks.
Yep.
All right,
Thank you.
well, we'll end it there, and everyone's welcome to join us later in the month where we'll be talking about cover crops. Thank you to both of our speakers, Stephen and Humberto. This was a great webinar today.
Thank you.
All right, bye, folks.